Welcome to Grandpa's Late Nights. Come in, come in. Pull the blanket up over your shoulders, the way you used to when you were small and the house had gone quiet and the only light left in the whole world was the little lamp by the bed. There, that's it. There's no hurry tonight. There's nowhere you need to be, and nothing you need to solve. And nobody's going to ask you a single question you have to answer. All you have to do, kiddo, is lie there and let your old grandpa talk, and let the words go soft and slow, like snow coming down outside a window you don't have to shovel. I want to tell you a story tonight. It's a big one, so we'll take it gently, a little at a time, the way you'd eat something warm on a cold night. Spoonful by spoonful, and you don't have to remember any of it. That's the wonderful thing about the middle of the night. Nothing you hear now has to be carried anywhere. If you drift off before I'm done, that's not a failure, that's the whole point. That's you doing it right. So let me start with a number, just one small number, and I promise I'll say it as softly as I can. Because it's a gentle little thing, even though it holds up everything you've ever seen or touched or loved. The number is 0.007, 7 thousandths. Or, if you'd rather hear it another way, 7/10 of 1%. That's smaller than the tip you'd round up on a cup of coffee, smaller than the crust you'd leave on the plate. And yet, kiddo, that tiny number is one of the reasons there is a you at all, lying there in the dark, breathing slow, listening to an old man's voice. Let me tell you what it is, and I'll do it the way I'd explain anything, with something you already know. You've heard of the sun. Of course you have. Everybody's felt it on the back of their neck on a summer afternoon. Now the sun is a great burning ball, and what it's doing up there mostly is taking the very lightest stuff in the universe, hydrogen, the simplest little building block there is, just about the smallest, plainest thing that exists, and it's squeezing it so hard, under so much weight, that 4 of those little hydrogen pieces get mashed together into one slightly heavier piece. A thing called helium. Same helium that's in a birthday balloon. Nothing scary. And here's the marvellous part, the part I want you to hold on to as you sink deeper into that pillow. When the sun does that squeezing, when it turns hydrogen into helium, the finished helium comes out just a hair lighter than the hydrogen that went in. A tiny bit of the mass simply isn't there anymore. Where did it go? It became light. It became warmth. It became the sunbeam that lands on the kitchen floor where the cat likes to sleep. That missing weight didn't vanish. It turned into the energy that pours out across 93 million miles of empty space and touches your face. And the amount that turns into light, the fraction of the hydrogen's weight that gets released as pure warmth, that, kiddo, is our little number. 0.007. 7/10 of 1% of the hydrogen's mass becomes the shine of the star. Now here is the part I want you to feel, slowly, without any alarm, because there's nothing to be alarmed about lying safe in your bed. That number could have been different. Nothing about the world we know says it had to be exactly 7 thousandths. And people who spend their whole careers thinking carefully about these things, patient people with pencils and long afternoons and quiet offices, they've asked a simple question. What if it weren't 7? What if it were a whisker smaller or a whisker larger? If you nudged it down, just a touch, down to about 6 thousandths, 0.006, then the very first step. The very first little handshake between 2 of these building blocks, the step where a proton and a neutron try to grab hold of each other and stick, that handshake would fail. They wouldn't bind. And if that first grip doesn't hold, the whole ladder of star building never even gets its bottom rung. You'd have a universe full of hydrogen and nothing else. Just the plain stuff, drifting forever, never cooking into anything richer. No helium worth speaking of, no carbon down the road, which means no wood, no leaves, no bones, no you. Just an endless, quiet fog of the simplest thing there is. And if you nudged it the other way, up to about 0.008, 0.008, then the opposite trouble. The hydrogen would be too eager. It would fuse too readily, grab hands too easily, and in the wild hot minutes right after everything began, it would all get burned up at once, used up, gone. Consumed in the first rush. And then there'd be no hydrogen left over. No hydrogen means no water, because water, remember, is just hydrogen holding hands with oxygen. And it means no long, slow, patient stars either, because a slow star needs a big reserve of hydrogen to sip at over billions of years. So there's our first little number, sitting in its narrow window. 0.007. Not 6. Not 8. Right in that soft middle where a star can burn gently and a universe can slowly fill up with the makings of things. Isn't that something to lie and think about? That the warmth on your face and the water in your glass hang on 0.007%. Now, I told you this was a big story, and I meant it, so let me open the door a little wider, still nice and slow, because it isn't just that one number. That's the thing I want to walk you through tonight, and there's no rush at all. We've got the whole quiet night. It turns out that our little 0.007 is not alone. There's a small handful of numbers like it, numbers built into the deepest floorboards of reality, the constants, the settings, the dials, whatever gentle word you like. And each one of them seems to sit in its own narrow window, its own soft middle, and if you were to reach in and turn any one of them, even a little, you might get a universe where no star ever forms, or no atom ever holds together, or no chemistry ever happens, and therefore no life, no planet, no porch, no grandpa, no you. A small number of dials, a small number of settings, and whether any universe worth the name can exist at all seems to depend on all of them landing where they landed. That's the story. That's the whole gentle, staggering story I'm going to lay out for you, one number at a time, over this long, soft night. And I promise you this, I'm going to be honest with you the whole way. I'm going to tell you which parts are solid, measured, weighed and checked fact, and which parts are the places where even the cleverest people have to shrug and admit they're guessing. Because you deserve the truth more than you deserve a tidy ending, and honestly, the truth is the more restful thing anyway. There's a great peace in a person who'll just tell you plainly what they know and what they don't. Now this idea, this notion of a small set of crucial numbers, it has a name, and a face, and a book. And I'd like you to have them, because it's nicer to hear a story when you know whose hands it passed through. There was a man named Martin Rees. He's English, and he holds a lovely old title, Astronomer Royal, which is exactly the sort of title that sounds like it belongs to someone who spends his evenings looking up. And back in 1999, going into the year 2000, he wrote a little book, and he gave it the plainest, warmest name you could ask for. He called it Just 6 Numbers. Just 6. That's the promise right there in the title. He said, in effect, look, if you want to understand the deep shape of the whole cosmos, you can hang an awful lot of it on just 6 settings. 6 numbers that shape everything. And he gave them names, or letters really, the way physicists like to. I'll say them softly, and you don't need to keep them straight. They're just going to wash over you like names read off a train timetable in a language you half know. There's N. There's a Greek letter, epsilon, that's our 7,000ths, the one we just met, the fraction of hydrogen that becomes light. There's omega. There's another Greek letter, lambda. There's Q. And there's D, which is the simplest of all, and we'll get to it, and it'll make you smile. N, epsilon, omega, lambda, Q, and D. 6 numbers. And the fellow's whole gentle argument was that these 6, sitting where they sit, are what make a universe that can hold stars and galaxies and eventually living things, instead of a universe that's dead on arrival, too fast or too smooth or too weak or too strong, or made only of the plainest fog. Now, I want to be straight with you here, because I said I would. And because it's the kind of honesty that actually lets a person rest easier. That word 6 is a lovely, clean number. It fits on a book cover. It's easy to hold in your head as you're falling asleep. But it isn't handed down from on high, and it isn't the only way to count. Martin Rees chose those 6 because they tell the story beautifully, because they're the ones that shape the big things, the stars, the galaxies, the reach of it all. Another physicist, counting a different way, digging into the smaller machinery, into the tiny pieces that make up the pieces, would tell you the real tally of these fundamental settings runs higher. In the great rulebook that describes the tiniest bits of matter, physicists call it the Standard Model, which is a very modest name for the most precisely tested description of nature we've ever written down. In that rulebook there are something like 26 of these free numbers. 26 dials that the theory itself can't explain, that we simply had to go out and measure, the way you'd measure a room before buying the carpet. So 6 is a beautiful curated handful chosen by a wise man to tell a clear story. It is not a claim that the universe runs on exactly 6 knobs and no more. I tell you that not to spoil the magic survives just fine, but because I'd rather you drift off holding something true than something merely tidy. And you can hold both, really, 6 numbers to tell the story by. More than 6 if you open the whole cabinet. Both are right. Rest easy on that. All right, let me take you to the first of Rees's 6 now, the one called N. And it's a big one, and it's a strange one, and it's the sort of thing that once you've heard it, you look at the night sky a little differently. Though there's no need to look at anything tonight but the inside of your own eyelids. N is about 2 of the great forces of nature and how they compare. Now don't tense up at the word forces. A force is just a push or a pull. That's all. When you drop a spoon and it falls to the floor, that's a pull, that's gravity, tugging the spoon down toward the middle of the earth. Gravity is the pull that keeps you in your chair, keeps the moon circling us, keeps the whole heavy business of the cosmos from flying apart. You know gravity in your bones. Every time you've ever been tired, every time your eyelids have gotten heavy the way they might be getting heavy right now. Some little part of you has felt grateful to gravity for letting you sink down into a bed instead of floating off the mattress. And there's another force, a different kind of push and pull, called electromagnetism. That's a longer word, but it's a friendly thing, honestly. It's the force that makes a magnet stick to the refrigerator. It's the force that makes your hair stand up when you pull off a wool sweater in winter. It's the force that holds the tiny pieces of every atom in your body together, and holds atoms to their neighbours, so that your hand is a hand and not a puff of loose dust. Electromagnetism is the great sticker together of small things. It's what makes the chair solid enough to sit on. When you knock on a table and it goes knock instead of letting your knuckles pass right through, that's electromagnetism saying, no, this is here, this is real, this holds. Now here's the question N asks, and it's a lovely simple one. Take two of the tiniest specks of matter, two protons, two little grains from the heart of an atom. They both feel gravity, pulling them together, ever so faintly. And they both feel electromagnetism, in this case pushing them apart, because they carry the same kind of charge, and like charges shove away from each other. So the question is, how do those two forces compare in strength? If gravity's pull is 1, how big is the electric push? And the answer, kiddo, is a number so large I almost don't want to say it out loud in a quiet room, for fear of waking you with its size. The answer is about 10, with 36 zeros after it. A 1, and then 36 zeros. 10,000, million, 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 million. That's how much stronger electromagnetism is than gravity between those two little specks. Let me say that a gentler way, because the number's too big to feel. Gravity, the force you know so well, the force that makes you tired, the force that holds up the mountains and swings the planets, gravity is, down at the level of the tiniest things, absurdly, almost comically weak. It is a trillion, trillion, trillion times weaker than the other force. Say that slowly to yourself as you breathe. A trillion, trillion, trillion times weaker. Now, you might think that's a defect. You might think, well, that seems careless, that seems lopsided. Why would nature make one of her forces so feeble? And this is my favorite kind of turn in a story, the kind where the thing that looks like a weakness turns out to be exactly the gift. Because that very weakness of gravity is why you get to exist at all. Let me tell you why, and I'll tell it slow. Think about a star again. A star is a titanic ball of that simple hydrogen, and it holds itself together by gravity, all that gas pulling on all that gas, squeezing down toward the center. And down in that center, the squeezing gets so fierce that the fusion begins. The handshake we talked about, the turning of hydrogen into helium and light. So gravity is the thing pressing down, trying to crush the star smaller, and the light and heat pushing out is the thing holding the star up. A star is a slow, patient argument between crushing and shining, and it lasts as long as that argument stays balanced. Now, and here's the beautiful part. Because gravity is so unbelievably weak, it has to gather up a truly enormous amount of gas before its feeble little pull adds up to enough weight to start the fire in the middle. It takes a mountain of hydrogen, a mountain the size of a sun, before gravity's whisper becomes a shout loud enough to light the core. And once it's lit, that same weakness means the star burns slowly. It sips its fuel. It doesn't gulp. Because gravity is squeezing so gently, the fire only needs to push back gently, and so it burns low and steady and long, for billions upon billions of years. Long enough for planets to cool and settle, long enough for oceans to form on one of them, long enough for something in one of those oceans to stir, and then, over ages you couldn't count if you tried all night, to become a fish and a creature that crawled onto land and a thing that stood up and looked at the sky, and finally, at the very tail end of all that patience, a grandpa and a kiddo and a warm bed and a soft voice in the dark. All of it, all that unhurried time, is a gift from the weakness of gravity. From N. From that number with 36 zeros. Because imagine, just for a moment, that gravity were stronger. Not a trillion, trillion, trillion times weaker, but only, say, a million times weaker, still weak, but much stronger than it really is. Then a star wouldn't need such a mountain of gas to light up. A little heap would do, and the stars that formed would be small, and they'd burn hot and fast and furious, guttering out in a geological blink instead of a cosmic age. They'd flare and die before anything on any planet had time to so much as become interesting. There'd be no long, slow afternoons of evolution. No time. The candle would be a match instead, flaring bright and gone. And a match doesn't warm a house through a long winter. Only the slow, low fire does that. Only the weak gravity fire. So there's N. Gravity, a trillion times gentler than the force that holds your atoms, and that very gentleness buying us all the time in the world. I do love that one. The weak thing turned out to be the patient thing, and the patient thing turned out to be the reason we're here. There's a lesson in it, maybe, but it's too late at night for lessons. Just let it sit warm in your chest. So now we've met 2 of the 6. We've met epsilon, our 7,000ths, the sliver of hydrogen that becomes light, and we've met N, the weakness of gravity that lets the stars burn slow and long. 2 dials, each in its narrow window. Each one, if you turned it, capable of erasing everything. And I've still got 4 more of Rees's 6 to bring you, and a good deal else besides, some of it stranger than what we've done so far, so we'll keep going nice and easy through the night. But before I carry us on, I want to plant something in the dark for you, a little seed of a mystery. I'm not going to answer it now. I'm going to let it sit way at the back of the story, and we'll come back around to it much later, once you're good and drowsy, and by then it'll have grown into the most peculiar thing of the whole night. That's how the old stories work. You lay a thread down early, and you don't pull it tight until the end. Here's the seed. Of all these numbers, these 6 of Rees's, and the 24 more in the deeper rulebook, there is one that stands apart from the rest. One that isn't just tucked into a narrow window, but sits in a place so strange, so far from where our finest thinking says it ought to be, that it has been called, and I'm not exaggerating for effect, the single worst prediction in the whole history of physics. That's the phrase they use, the worst prediction ever made. And I don't mean worst as in a small mistake, a rounding error, a decimal in the wrong spot. I mean that when our best theories sit down and calculate what this one number ought to be, and then we go out and actually measure what it really is, the 2 answers disagree, not by a little, not by double, not by 1,000 times, but by a factor of 1 followed by 120 zeros. 120 zeros. Kiddo, I can't even offer you a picture for that one yet, and I won't try, not tonight, not this early. It's too big and too strange, and it deserves to be crept up on. All I'll tell you for now is its letter. It's lambda, another of Rees's 6. And in plainer words, it's the thing that decides whether the whole universe, having been born and spread out, keeps drifting apart gently forever, or comes flying apart too fast for anything to ever gather together, or perhaps falls back in on itself and never gets started at all. It's the push built into empty space itself. The push in the nothing. And our best calculation of that push is wrong by 120 zeros. And yet, here's the thread I'm leaving hanging, here's the thing to fall asleep wondering about, and yet the real value, the true measured value, the one nature actually chose, lands in just about the only narrow slot where galaxies could ever have formed, where anything could gather, where you could happen. How? How is our proudest, most careful calculation off by more than any calculation has any business being, And how does the real answer, nonetheless, come out exactly gentle enough for a cosmos to fill with stars and settle down and grow a person who lies in a warm bed at night? I'm not going to tell you yet. I want you to carry that little unanswered thing down with you into the deeper part of the evening. We'll come back for it, I promise. Grandpa always comes back for the thread he laid down. But not yet. For now, let's just rest for a moment in what we've already gathered, because it's plenty, and there's no need to hurry to the next thing. Let it settle like sediment in still water. We started with the smallest, softest number I could find, 7/1000ths, the fraction of a hydrogen atom's weight that becomes light when a star does its slow work, and how, if it were 6/1000ths, the fire would never catch, and if it were 8/1000ths, the fuel would all be spent in the first rush, and either way you'd have no water, no long stars, no us. Then we met a man, Martin Rees, the Astronomer Royal, and his gentle little book called Just 6 Numbers, and his 6 letters, N and epsilon and omega and lambda and Q and D, and we were honest with each other and admitted that 6 is a beautiful chosen handful rather than the whole cabinet, which holds more like 26 dials all told. And that's fine. Both things are true, and both can rest easy in the same night. And then we sat with N, the almost unbelievable weakness of gravity, a trillion times gentler than the force that holds your hand together, and we found that its weakness is the very reason the stars can afford to burn slow and long, sipping their fuel across billions of years, buying all the unhurried time it took for a warm little world to cool and for life to stir on it and, eventually, for you. That's a lot to have carried in, and you carried it beautifully just by lying there and breathing. You don't have to do anything with any of it. The knowing isn't the point. The point is just to be here, warm, in the dark, while an old voice lays these enormous gentle things out one by one. Like a grandfather emptying his pockets on the kitchen table at the end of a long day. Here's a stone I found. Here's a bit of string. Here's a number that holds up the sky. And I've got so much more for you, kiddo. There's the strange business of a tiny difference in weight between 2 of the smallest specks there are, a difference of about 14/100ths of 1%, and how every single atom in your body depends on that little imbalance falling exactly the way it fell. There's a man who, back in 1953, sat down and predicted, purely from the fact that he himself existed and was made of a certain stuff, that a very particular hidden rung had to be tucked away inside the carbon atom, a rung nobody had ever seen. And then they went and looked, and there it was, right where he said. There's the fragile little bond, the first rung of the whole ladder of fire, so delicate it's held together by the faintest whisper of a force. And there's that 120 zeros mystery waiting patiently at the back of the room for us to come around to it once you're nearly gone. But all of that is for the deeper hours. Right now there's nothing to do and nowhere to be. The number is 7/1000ths, and it lets the sun shine on the kitchen floor. Gravity is a trillion times weaker than it might have been, and that weakness is a kindness that gave us all our time. And somewhere out past the edge of everything, one strange number sits 120 zeros away from where it ought to be. And somehow, impossibly, it landed just gentle enough to let a universe hold together long enough for me to sit here and tell you about it. Breathe in, slow, and out, slower. There's no test at the end of this. There's no morning you have to be sharp for that can't wait a while. There's just the dark, and the blanket, and the low warm fire of an old man's voice, and 6 little numbers that had to fall just so, and did, and here we are because of it. Stay with me a while longer if you can. And if you can't, if you're already halfway down into sleep, if the words are starting to blur and come apart at the edges like sugar in warm tea, then that's all right too. That's just fine. Let them blur. Let them come apart. The numbers will still be here when we pick the story back up. And so will I. And so will the porch light, glowing soft out there in the dark, keeping watch while you rest. Now let me tell you about that little difference in weight, the 0.14%, because it's one of the tenderest things in the whole story, and it's exactly the sort of small, quiet fact that belongs to the middle of the night. It begins, as so many of these do, deep down inside the atom, in that little crowded heart we call the nucleus, where the protons and the neutrons live packed together like eggs in a carton, the proton and the neutron. Two little things. They look almost like twins, if you squint at them from far enough away, both sitting in the nucleus, both roughly the same heft, both doing the quiet structural work of holding an atom together. But they are not exactly the same, and the difference between them, once you know what to look for, turns out to be one of the most load-bearing facts in all of nature. The neutron is heavier than the proton. Not by much, not by anything you could hold in your hand and feel the difference of. It is heavier by 293 MeV, that is 1.293 million electron volts, which sounds like a lot until you know that a neutron itself masses about 99.565 of those units, and a proton masses 938272. The gap between them, that slim 1.293, is 0.14% of a nucleon's mass. You know what 0.14% looks like in everyday life? It is the weight of a single grain of rice against a small handful. It is the thickness of a coat of paint on a wall compared to the wall itself. It is nothing. It is less than nothing. It is a whisper of difference barely there at all. And yet the entire architecture of ordinary matter rests on it. Here is why. Because the neutron outweighs the proton by that tiny margin, the neutron is unstable on its own. Left to itself, free of a nucleus, a neutron does not simply sit quietly. It decays. It falls apart. It lives, on average, somewhere around 880 seconds before it gives up and converts itself into a proton, releasing an electron and a little ghost of a particle we call an antineutrino. 880 seconds. Not years, not days, 14 minutes and change. Left alone, every free neutron in the universe would dissolve in roughly the time it takes to walk to the corner store and come back. Now that sounds catastrophic, and in the right circumstances it is. But here is where the story gets quiet and careful. Inside a nucleus, neutrons are a different matter. Packed in close with protons, bound by the strong nuclear force, they stabilize. They stay. The nucleus holds them. It is only the lonesome, unattached neutron, the one not invited into a nucleus, the one out on its own in the open, that ticks down toward dissolution. And that distinction between the neutron inside and the neutron alone turns out to matter enormously for what happened in the first few minutes of the universe's life. We will get there. For now, hold the number. 880 seconds. 14 minutes. Approximately, that is how long a free neutron lasts. Now turn the dial. Imagine the neutron were lighter than the proton instead. Just reverse it, proton on top, neutron on the bottom, by that same tiny margin. What happens? If the neutron were lighter, the proton would be the unstable one. The proton would decay, And if protons decay, hydrogen atoms cannot exist. Because a hydrogen atom is just one proton with one electron around it, there is nothing else, no neutron, no complexity, just that single proton in the center. Take away proton stability and you lose hydrogen. And without hydrogen, you lose water, which is two hydrogens and an oxygen. You lose the vast oceans and the slow rivers and the morning dew on a spider's web. You lose the fuel that ordinary stars like our sun burn for billions of years. You lose the chemistry of living things, which is built almost entirely on carbon chains wrapped in hydrogen and oxygen and nitrogen. All of it ultimately traceable back to that one stable proton holding its electron close. The whole ordinary world, everything you can see and touch and smell, every warm thing, every wet thing, every breathing thing, requires proton stability. And proton stability requires the neutron to be the heavier of the two, by roughly 1.293 MeV, by 0.14 of 1%. But now look the other direction. What if the gap were much larger? What if the neutron outweighed the proton, not by a tiny sliver, but by a substantial amount, say, several MeV more than it does? Then something else breaks. In the first minutes after the Big Bang, as the universe cooled enough for protons and neutrons to start combining into simple nuclei, a too heavy neutron would decay faster. Or the mass gap would become large enough that primordial neutrons converted into protons almost instantly, before they ever had a chance to be incorporated into deuterium and then helium. You would end up with a universe of almost pure hydrogen and almost nothing else. No helium. No heavier elements, no pathway forward to carbon, to oxygen, to iron, to anything. So the window is narrow in both directions. The neutron has to be heavier than the proton, but not by too much, and not too little. It has to sit in a slim corridor of possible values where free neutrons last long enough to build helium before they decay, but where the proton remains stable enough to anchor hydrogen forever. And it does. It sits there. It has always sat there, at 1.293 MeV, as patient and exact as a key cut to fit a particular lock. Now here is the part that goes deeper still, and this is what the title was hinting at when it mentioned the mass of a quark. Because the neutron and the proton are not fundamental particles themselves, they are made of smaller things. Quarks, 3 of them apiece, jostling around inside each nucleon in combinations that physics worked out through decades of increasingly powerful experiments. A proton is 2 up quarks and 1 down quark. A neutron is 1 up quark and 2 down quarks. And the masses of those quarks, the up quark and the down quark individually, are what ultimately set the balance between the proton and the neutron. The up quark has a mass of roughly 2.2 MeV. The down quark has a mass of roughly 4.7 MeV. The down quark is heavier. That is why the neutron, which contains 2 of the heavier down quarks, winds up heavier than the proton, which contains 2 of the lighter up quarks. The gap between those quark masses, about 2.5 MeV, combined with a small electromagnetic contribution, produces that 1.293 MeV advantage the neutron has over the proton. So when you ask why the neutron outweighs the proton by 0.14 of 1%, the answer, at the bottom, is that the down quark happens to be about 2.5 MeV heavier than the up quark. That is the actual load-bearing number. 2.5 millionths of the energy in a proton's rest mass. A hair on a hair. In 2008, the physicists Thibault Damour and John Donoghue mapped out what would happen if you slid those quark masses around if the up quark were heavier, or the down quark lighter, or the gap between them different in any number of ways. What they found was a narrow viable window. Shift the up and down quark masses by even an MeV or two in the wrong direction, and you can unbind the proton or destabilize the neutron entirely. The specific numbers that nature chose, up quark at 2.2, down quark at 4.7, sit in the middle of a corridor that permits stable matter. Outside the corridor, ordinary atoms dissolve. And without atoms there is no table, no chair, no sleeping body, no mind to wonder about any of it. It is a strange thing to sit with in the dark. The up quark and the down quark, with their particular masses, their particular small heavinesses, are not things you can point to or photograph or feel. They are not things that have names in ordinary language the way chairs and rivers do. They are abstract. They are deep. They are the hidden bones of everything you have ever touched, and they sit at values that permit matter to hold together. And they did not have to. Let me give you an image to hold on to. Imagine you are stringing a hammock between two old trees. You need just the right tension, tight enough to hold your weight, loose enough not to pull the trees together and topple them. If the rope is too slack, the hammock sags to the ground and you are sleeping in the dirt. If it is too taut, the whole thing snaps and you end up in the dirt anyway. The 2.5 MeV difference between the up quark and the down quark is the tension in the rope. It is set to the value that lets the hammock hang. And you are lying in it right now, even if you cannot feel the rope. Breathe a little slower with me. The pillow is still there. The dark is still around you. We are not rushing anywhere. We are just walking, gently and slowly, through the deep rooms of the universe. Now, the quarks have their masses. The neutron is slightly heavier than the proton. And roughly 3 minutes after the Big Bang, something happened with that arrangement that determined the broad shape of the universe for all time to come. Big Bang nucleosynthesis, it is called. It is a big phrase for a short and decisive event. In the early universe, the temperature was so extreme, billions of degrees, not millions, billions, that protons and neutrons could not yet stick together. Any deuterium nucleus, a proton bonded to a neutron that tried to form immediately got blasted apart by the roaring photons around it. It was too hot, too dense with radiation for anything complex to survive. So the particles just sloshed around free, converting back and forth between proton and neutron as the temperature permitted. But the universe was expanding, cooling, and as it cooled, the furious photodissociation slowed. Around the first few minutes of cosmic time, the temperature dropped enough that deuterium could finally survive being formed. And the moment it could, the whole story accelerated. Deuterium caught a proton and became helium-3. Helium-3 caught a neutron and became helium-4. And within a window of a few minutes, the entire light element budget of the universe was more or less set. The result was this: roughly 75% of all ordinary matter in the universe, by mass, emerged from those first minutes as hydrogen. The remaining 25%, approximately, emerged as helium-4. A trace of lithium appeared as well, a small chemical footnote at the end of the ledger, and that was the inventory. Hydrogen and helium, 3 parts to 1. Everything else that has ever existed, carbon, oxygen, nitrogen, iron, gold, silicon, the calcium in your bones, the iron in your blood, was not there yet. It had not been made yet. The universe was born simple. The complexity came later. cooked in the hearts of stars over billions of years. But those stars needed hydrogen to burn, and that hydrogen was assembled in the first few minutes, and the ratio of hydrogen to helium was decided in large part by that 1.293 MeV mass gap between the neutron and the proton. Here is the thread. When the universe was a few seconds old and cooling through billions of degrees, the ratio of neutrons to protons was being set by the balance of their masses and the temperature of the surrounding soup. At some point, the conversion reactions froze out, they could no longer keep up with the expansion, and the ratio locked in at roughly 1 neutron for every 7 protons. 1 to 7. Then the neutrons started to decay. Remember, free neutrons live about 15 minutes. In those first few minutes, before nucleosynthesis was complete, some fraction of the free neutrons simply dissolved back into protons. So the ratio shifted slightly by the time the fusion window opened. But not too much, because that fusion window opened fast enough that most of the neutrons were swept up into helium nuclei before they had time to decay, but slowly enough that a few did. The free neutron lifetime, that 15-minute clock, shaped the outcome. If neutrons lasted for only a few seconds, they would all decay before getting incorporated, and you would get a universe of pure hydrogen. If they lasted for hours, the neutron-to-proton ratio would barely shift, and you would get too much helium. The actual 15 minutes sits in the middle, producing the 75-25 split that stars need, and that living chemistry builds upon. So the neutron lifetime is itself tuned seeming. 15 minutes, not 2 minutes, not 2 hours. 15 minutes, give or take, because of the way the weak nuclear force couples to those quarks, which in turn traces back to the mass difference between up and down, which traces back to whatever sets quark masses in the first place, and that last question connects to the Higgs field, which is its own vertiginous drop, and we will touch that later tonight. For now, 75% hydrogen, 25% helium. Those are the raw materials the universe handed to the first generation of stars. That is the starting inventory from which every atom in your body was eventually built. And the fact that hydrogen survived in such abundance, the fact that the universe did not burn through all its hydrogen in the Big Bang and leave nothing for stars to feed on for billions of years, required the neutron to outweigh the proton by that exact, slender amount. Close your eyes a moment, if they haven't already closed. There is something almost comforting in this, I think. Not in the numbers themselves, which are vertiginous if you stare at them too long, but in the scale of the patience involved. The universe spent the first 3 minutes setting its ingredient list, and then it waited. Billions of years, stars living and dying, elements being forged and scattered, before the conditions assembled themselves into something that could wonder about any of this. There was no hurry. There never is. The deep processes run slowly, and the dark is patient. Now, let me tell you about Fred Hoyle. Fred Hoyle was born in 1915 in a small Yorkshire village called Gilstead, and he had the kind of mind that found conventional scientific careers slightly chafing, not because he lacked rigour, but because he had an almost uncomfortable willingness to follow an idea past the point where other people got nervous. He was wrong about several famous things, bluntly and publicly wrong. And he was right about several others in ways that took decades to be properly recognized. The one I want to tell you about now sits in a particular place in the history of science because of how he derived it. By the early 1950s, Hoyle had been working on the problem of how stars make the elements. The hydrogen and helium from the Big Bang were the raw material, But the universe around us is clearly full of heavier elements, carbon above all, because life on Earth is built on carbon chemistry. Carbon atoms are everywhere in biology. Your body is mostly water and carbon compounds. The cells that are keeping you alive right now, the proteins and fats and DNA, are carbon scaffolding hung with hydrogen and oxygen and nitrogen. So the question was, where does all that carbon come from? It has to be made somewhere. And the obvious candidate was stars. Stars are enormous nuclear furnaces. They fuse lighter elements into heavier ones. The process for making helium from hydrogen was understood. The next step, from helium to carbon, required fusing 3 helium-4 nuclei together, 2 of them first, to form beryllium-8, and then a third helium colliding with that beryllium to produce carbon-12. The trouble was beryllium-8. It is fantastically unstable. It falls apart in about 10 to the negative 16 seconds, 100 quadrillionths of a second, which means the chance of a third helium arriving to collide with it before it dissolves is incredibly small. The process seemed, on paper, far too slow to account for all the carbon in the universe. Hoyle saw a way out. If carbon-12 had an excited state energy level, an internal resonance, sitting at just the right energy above the ground state, the process would be enormously accelerated. A quantum resonance, in nuclear physics, is something like a note that a nucleus can hum at. It is an energy level at which the nucleus is temporarily, briefly, just right to absorb incoming energy. If the carbon-12 resonance sat close to the energy that 2 helium-4 nuclei and 1 beryllium-8 nucleus sum up to, the reaction would happen far more readily, the way a wine glass vibrates when a singer hits the right note, and carbon could be produced in the quantities we see. The energy of 3 helium-4 nuclei combining, accounting for the brief instability of beryllium-8, worked out to approximately 7.65 MeV above carbon-12's ground state. So Hoyle predicted in 1953 that carbon-12 must have an excited state energy level at approximately 7.65 MeV. Not from an experiment, not from observing it, from the fact that carbon exists in the universe, and that he, Fred Hoyle, was made of it and was alive and thinking. It is one of the most unusual derivations in the history of science. He did not measure the carbon nucleus and find the resonance. He looked at the finished universe, noted that carbon was everywhere and life existed, and worked backward to the conclusion that the nuclear physics must be set up in a specific way to permit it. It is reasoning from effect to cause. It is looking at the watch and inferring the watchmaker's mechanism without having seen the mechanism, except in this case there is no watchmaker implied, just the quiet logic of an existence argument. We are here. Carbon is here. Therefore the resonance must exist. He went to the Kellogg Radiation Laboratory at Caltech, where William Fowler and his group did the experimental work on stellar nucleosynthesis. He told them what he expected to find and asked them to look. And they found it, an excited state of carbon-12 at 7.654 MeV, not 765 exactly, 7,654, but well within the neighborhood Hoyle had specified. Close enough to the combined energy of the 3 helium system to allow the triple alpha process to proceed efficiently in stellar cores. 7.654 million electron volts. It was there, sitting inside carbon-12, exactly where Hoyle had said it had to be, for the reason that the universe had to be capable of making carbon, for the reason that carbon had to be capable of making life, for the reason that life had to be capable of making a Fred Hoyle who could sit in England and reason backward through the layers of nuclear physics to the thing that had to be true. Fowler was awarded the Nobel Prize in Physics in 1983, partly for this work. Hoyle was not, a matter of ongoing controversy in the history of science. But what the two of them together established, Hoyle's prediction and Fowler's experimental confirmation, is one of the genuine moments in 20th century physics where the fine-tuning problem becomes not an abstraction but a specific, measured, verified number. Because the resonance did not have to be at 7.654 MeV, the strong nuclear force, the force that binds quarks into protons and neutrons into nuclei, sets these energy levels, and there is no apparent reason from first principles why the strong force had to be tuned to produce a carbon-12 resonance at that value rather than any other. It could have been a few tenths of an MeV different, and if it were, the triple alpha process would fail. Or the competing reaction that turns carbon into oxygen would dominate, and the universe would have far less carbon in it than it does. How sensitive is it? Oberhammer, Sixt, and Schlattl worked out in 2000 that a change of roughly 0.5% to 4% in the strength of the strong nuclear force would drastically alter the ratio of carbon to oxygen produced by stars. Too far in one direction and stars make almost exclusively carbon. Too far in the other and they make almost exclusively oxygen. Either way, the specific mix that life depends on, carbon scaffolding, oxygen for the bonds, and for breathing, both present in generous abundance, would not emerge. The window is narrow. A few percent on the strong force. Inside that window, you get the universe we have. Outside it, you get something sterile. Or at least something that cannot produce the chemistry of living things as we understand it. Now, I want to be careful here, because this is exactly the kind of place where popular treatments overstate the case, and the title of this video asked us to be honest about where the solid science ends and the interpretation begins. The Hoyle resonance itself, 7,654 MeV, is a measured, verified fact. It is T1, the bedrock. The calculation that shifting the strong force by a few percent would wreck the carbon to oxygen ratio, that is a more model-dependent result. T2 in the language of my notes to myself, meaning it is the output of theoretical calculations that are respected and widely cited, but which involve assumptions and simplifications that real nuclear physics does not let you fully escape. The 0.5 to 4% figure is Oberhammer's estimate, not a final verdict. Other groups doing related calculations have found different specific numbers. What remains robust, even after the caveats, is this: the energy levels of nuclei, which are set by the strong force, are not infinitely adjustable without consequence. The triple alpha process that makes carbon works because the relevant energy levels happen to nearly coincide. Move them substantially, and the process fails. How substantially is not precisely agreed upon, and that matters. But the coincidence is real, and the coincidence was noticed by Fred Hoyle. And he bet his scientific reputation in 1953 that an energy level had to be there because we exist. And it was. That is remarkable regardless of what you think it means. And what does it mean? That is the question, and it is the one we are saving for the second half of tonight's walk. But I want to plant a marker here before we move on. The Hoyle resonance is one of the clearest examples in physics where the fine-tuning problem has a specific, concrete, experimental handle. It is not just gravity seems convenient. It is, here is a number, 7,654 MeV, measured in a laboratory that had to be approximately what it is for stars to make the carbon that you are built of. That is either a remarkable coincidence, or evidence of something beyond coincidence, or a consequence of some deeper constraint we do not yet understand, and those three options, in order, map onto the three honest responses physicists give to the fine-tuning problem as a whole. We will get there. For now, the number. 7,654 MeV. Hold it lightly in your mind. The dark is still good out there. You can hear the night if you listen past the narration. I like to think of it as breathing. The night, a slow rise and fall that has been going on longer than anything else. The same dark that was there when the Big Bang nucleosynthesis was setting the hydrogen to helium ratio. The same dark that was there billions of years later when the first stars were synthesizing carbon in their cores and the Hoyle resonance was doing its quiet, essential work. The dark is old. It does not mind the company. And if you are very nearly asleep right now, if the narration has gone from meaning to sound to a soft texture around the edges of consciousness, that is exactly right. That is where this kind of story is meant to be heard, at the threshold, where you are neither quite here nor quite gone, where the large things can settle in without your mind grabbing at them. There is one more loop I opened at the beginning of tonight that I want to return to, and it lives inside the triple alpha story, and it connects the Hoyle resonance to the deepest question of why the strong force produces the energy levels it does. The strong nuclear force, as physicists study it, is governed by a framework called quantum chromodynamics, a dense, mathematical theory of quarks and gluons. Within that framework, the specific energy levels of nuclei, like carbon-12, emerge from interactions so complex that they can barely be computed directly, even on the fastest computers. They are what they are, and what they are permits the triple alpha process to work. Whether they had to be what they are, whether some deeper principle fixes them, is exactly the unanswered question at the heart of the fine-tuning problem. Hoyle himself, later in his life, found the coincidence deeply suggestive. He wrote in a well-known passage that a common-sense interpretation of the facts suggests that a super-intellect had monkeyed with physics and also with chemistry and biology, and that there are no blind forces in nature worth speaking about. He did not say that lightly. He was not a religious man in any traditional sense. He was a physicist's physicist, rigorous and contrarian, and uncomfortable with easy answers. And yet, the carbon resonance, the thing he predicted from the fact of his own existence, led him to that conclusion. I am not telling you his conclusion is right. I am not telling you it is wrong. I am telling you it is honest. He followed the logic where it led him, and where it led him was to a place that could not be settled by experiment, which is itself part of the point. Now here is where the triple alpha process slots into the larger architecture of what we are exploring tonight. We began with epsilon, with that 7% of hydrogen mass that converts to energy in fusion, and I mentioned the open loop, the number that is off from prediction by 120 zeros, which we will reach. We also talked about N, the ratio of electromagnetism to gravity, that 10 to the 36 that gives stars their billions of years of slow burning. What the Hoyle resonance adds to this picture is a third layer, even once you have the hydrogen. Even once you have stars capable of fusing it on a long timescale, the subsequent manufacturing of complex elements, the chemistry of life, requires the nuclear energy levels to be arranged just so. You need the right fuel, you need the right furnace, and you need the right nuclear coincidences inside the furnace to turn simple fuel into complex chemistry. Three separate requirements, three separate dials, all set to values that permit the outcome. And so far we have not even touched the constants that set the large-scale structure of the universe, the density perturbations, the flatness parameter, the dark energy. Those are coming. But first, let me let you rest with what we have. The neutron outweighs the proton by 293 MeV, 0.14%. Because the down quark at 4.7 MeV is heavier than the up quark at 2.2 MeV, and that gap, tracked by Damore and Donoghue in 2008, sits in a narrow corridor that permits stable matter. The free neutron lives for roughly 880 seconds, about 15 minutes, and that lifetime set the ratio of neutrons to protons that survived the Big Bang's first minutes to become incorporated into helium before they decayed away. Big Bang nucleosynthesis produced a universe of 75% hydrogen and 25% helium by mass, with a trace of lithium. And that inventory became the raw material for all subsequent stars, elements, and chemistry. Fred Hoyle, in 1953, predicted from the bare fact of his own existence that carbon-12 had to have an excited state resonance at approximately 7.65 MeV. William Fowler's group at Caltech confirmed it at 7.654 MeV. The triple alpha process works because that number is what it is. And the calculation that changing the strong nuclear force by even a few percent would drastically alter the carbon to oxygen balance in stellar nucleosynthesis, the work of Oberhammer, Hist, and Schlattl in 2000, gives that coincidence an approximate quantitative edge, even if the precise boundaries remain model-dependent and contested. 4 facts. 4 quiet, heavy things to carry with you into sleep. The world outside is still. Nothing urgent is happening. Nothing needs solving. The numbers are old, billions of years old, and they have been sitting in their windows patiently the entire time, asking nothing of you, simply being what they are. You did not choose to be made of carbon, built on that triple alpha process. Sustained by the hydrogen from the first 3 minutes, held together by protons that remain stable because the neutron is the one that outweighs. You simply are. And the path that leads from the first quark masses all the way to you, lying there in the dark, is long and improbable seeming and real. Genuinely, verifiably, measurably real. Let the breath go slower now. The next part of the story, the large-scale architecture, the roughness of the universe that lets galaxies form, the flatness that had to hold to 15 decimal places, is waiting for us, patient as the dark. There is no hurry. There is only the quiet, and the numbers, and the warm sound of a voice that has been telling you things worth knowing at the end of the day. Sleep comes in when you are not watching for it. Like a lot of the best things. Let it. There is one more number I want to tell you about before we move to the larger picture. One more quiet, load-bearing thing sitting in the dark alongside everything we have already said. It is called the deuterium binding energy, and its value is 2.22 million electron volts. That sounds like a technical thing, a cold and clinical measurement from a laboratory somewhere, and I suppose in one sense it is. But in another sense, it is the most important handshake in the universe. Think of it this way. Everything that Hoyle found, everything that the triple alpha process accomplishes, the carbon, the oxygen, the atoms your body is made of, all of it requires that stars be burning in the first place. Stars burn by fusing hydrogen. And the first step in fusing hydrogen is 2 protons finding each other and one of them briefly becoming a neutron so they can stay together. What they form when they do that is called the deuteron. A proton and a neutron, hand in hand, the smallest composite nucleus in nature. It is also the first rung on the ladder. Without the deuteron forming, the ladder has no bottom. Fusion never starts. Stars never light. And everything we spent the last little while talking about, the triple alpha process, the Hoyle resonance, the careful balance of carbon and oxygen, all of it is moot, because the furnace never came on. The deuteron is bound by 2.22 million electron volts. That is not a large number by the standards of nuclear physics. Think of a pair of magnets that are just barely attracted to each other. Hold them at the right distance and they stay together. Move them a little and they drift apart. The deuteron is like that. It is the universe's most delicate partnership, committed enough to hold, fragile enough that a small change in the forces binding it would pull them apart and leave you with nothing but a cosmos of lonely protons drifting through the dark, never combining, never building anything heavier than hydrogen, never making the raw material for a star, a planet, a molecule of water. If the strong nuclear force were a few percent weaker than it is, the deuteron would not bind at all. That 2.22 million electron-volt handshake would drop below the threshold where the two particles can stay together, and they would part company immediately, every time, permanently. A universe where that is true is a universe of hydrogen only. Not hydrogen as a convenient fuel for stars, but hydrogen as the ceiling, the final answer, the end of the periodic table. Nothing else forms, nothing more complex than the simplest atom. The shelves of chemistry, empty, the blueprint for anything alive, unwritable, and if the strong force were a few percent stronger, the story goes the other way. Something called the diproton, two protons, would bind together without needing one of them to become a neutron. And if protons can fuse directly, the hydrogen in the early universe burns away almost immediately, in the first frantic moments after the Big Bang, before stars even have time to form. The hydrogen supply runs out before the universe builds anything to use it. Same result, opposite direction. The ladder still has no bottom, just for a different reason. 2.22 million electron volts, that is the measurement. The fragility of the handshake is the finding. And the finding is that the first rung of all the nuclear chemistry that ever made a star shine, or a planet cool, or a living thing breathe sits in a window narrow enough that, moving it by a small fraction, changes everything irreversibly. This is not poetic exaggeration. The physicists who work on this, who ran the calculations, who checked the numbers, are careful. Skeptical people who are professionally suspicious of coincidences. They are not given to drama, and they look at the binding energy of the deuteron and they say, that could have been different, and if it had been, we would not be here to know it. Let that one rest a moment. 2.22. The first rung. Small enough to break, real enough to hold. Now let me tell you about texture. Not texture you can touch. Texture in the fabric of the early universe itself. About 380,000 years after the Big Bang, a number that sounds enormous but is actually a blink, cosmically speaking, the universe cooled enough for electrons and protons to finally combine into neutral hydrogen atoms. Before that moment, the universe was a hot plasma, a dense fog, electrons and protons careening around so energetically that they could not stay together. Light could not travel freely through it. It bounced off the charged particles like flashlight beams in a thick mist. When the universe cooled enough for atoms to form, the mist cleared. The fog lifted. Light poured through. And that ancient light is still traveling, still reaching us, from every direction, stretched by billions of years of cosmic expansion into microwaves rather than visible light. We call it the cosmic microwave background, and we have mapped it in extraordinary detail. What the maps show is this. The cosmic microwave background is almost perfectly uniform. Almost. Point your microwave detector at one patch of sky, then another, then another. The temperature you read is almost exactly the same everywhere you look. The universe, in its early moment of first transparency, was almost perfectly smooth. Almost, not quite. There are tiny fluctuations, tiny variations in temperature from one patch of sky to another, tiny wrinkles in the otherwise smooth fabric. And those wrinkles, those almost imperceptible differences, are marked in the physics literature with a number called Q. And Q is approximately 10 to the power of -5. Written out, that is 1 followed by 5 zeros in the denominator, 1 in 100,000. The early universe was not perfectly smooth, it was smooth to within 1 part in 100,000. Those tiny wrinkles were the seeds. Imagine you have a very still pond, no wind, no current, almost no disturbance at all. But there is one. A barely perceptible ripple, not from anything dramatic, just from the natural quantum jitter of the early universe. The fact that on small enough scales, nothing can be perfectly, absolutely smooth. Quantum mechanics itself forbids the complete absence of fluctuation. So there were ripples, tiny ones, 1 in 100,000, and gravity, patient and persistent, began to work on them. Gravity does not care about the smoothness of the pond, it cares about the differences. It pulls where there is a little more matter toward the center of that little more matter. Over millions, then hundreds of millions of years, the regions that were slightly denser attracted more material, grew denser still, attracted more, grew still denser. The process is slow and relentless, like the way water running over stone does not seem to be accomplishing anything on any given Tuesday, but comes back 1,000 years later having carved a canyon. Gravity gathered the ripples into clumps. The clumps gathered into clouds. The clouds collapsed under their own weight into the first stars. And the stars gathered into the gravitational basins we call galaxies. All of that, every galaxy you have ever seen a photograph of, every spiral arm, every cluster of 100 billion suns, every nursery cloud of gas where new stars are forming tonight, came from those original wrinkles. From Q equaling approximately 1 in 100,000. Here is what Martin Rees's analysis suggests about what happens if you move that number. If Q were smaller, say 10 to the -6, which is 1 in a million, the ripples are even tinier, the density difference is even more subtle. Gravity still works on them, but the contrast is too faint. Gas clouds form, but they are too diffuse and too spread out to collapse into stars. The universe stays a kind of thin, cold fog forever. No galaxies, no stars, the lights never come on. And if Q were larger, say 10 to the -4, 1 in 10,000, the ripples are bigger. The density contrasts sharper, the early collapse much more violent. In that scenario, the clumps pull together too fast and too hard. Instead of settling into the sprawling, loosely bound structures of galaxies with billions of individual stars, matter crashes together into enormous concentrated masses. The dominant objects in the universe become giant black holes rather than sun-like stars scattered across galactic disks. There are stars of a kind in this version of history. but they form inside environments so turbulent and so radiation-drenched that the conditions for chemistry, for planets, for the slow, quiet work of biology are not available. 1 in 100,000. The roughness of the universe, measured to extraordinary precision from the ancient light. Big enough to seed structure, small enough to leave room for it to grow slowly into the varied, habitable architecture we find. Q sits in a window. Another one. Another case where the number is what it needs to be. And now we come to something that sounds almost too simple to matter. How flat is the universe? Not flat in the way a table is flat. Flat in a more abstract sense, in the sense of whether the geometry of space is curved toward itself, curved away from itself, or exactly balanced between the two. Think of the difference between the surface of a sphere and a saddle shape and a perfectly flat tabletop. A universe with too much matter curves like the sphere, space folds back on itself. Eventually, the expansion halts, and the universe recollapses in a big crunch. A universe with too little matter curves the other way, space opens outward, expansion accelerates without bound, and everything spreads so thin, so fast, that no structure can ever form. A universe that is exactly flat, balanced precisely at the critical density. Expands forever, but slows just gently enough that gravity can still do its work, still draw together the galaxies, the stars, the worlds. Physicists measure this with a quantity called omega, the Greek letter, sometimes called the density parameter. When equals exactly 1, the universe is flat. Less than 1 and it curves away. Greater than 1 and it curves inward. We measure today, and it is approximately 1. Beautifully, unnervingly 1. But here is where the story gets strange. Here is where the number opens into something that stops physicists in their tracks. To understand why being close to 1 today is remarkable, you have to think about what that means for the past. The universe expands. And in an expanding universe, any deviation from perfect flatness grows with time. If we're slightly more than 1 at the beginning, even slightly, the difference between its actual value and 1 would have grown larger and larger as the universe expanded. Conversely, if it were slightly less than 1, the flatness is not stable. It is unstable, like a pencil balanced on its tip. Any tiny nudge, and the pencil falls. Any tiny deviation from exactly 1 and runs away from 1 as the universe ages. So if is approximately 1 today, after 13.8 billion years of cosmic expansion, it had to have been much, much closer to 1 in the early universe. Working backward through the expansion tells you how close. 1 second after the Big Bang would have needed to equal 1 to within 1 part in 10 to the power of 15. That is 1 followed by 15 zeros in the denominator. 1 in a quadrillion. The density of the universe in its first second would have needed to match the critical density to 15 decimal places. And if you go back further, to the Planck time, which is the earliest moment that current physics can meaningfully address, a time so short after the Big Bang that our equations of space and time themselves may not hold, the required precision becomes 1 in 10 to the power of 60. That is 1 followed by 60 zeros. A number so precise that any analogy I can give you will fail before it gets close. I will try anyway. Imagine throwing a dart at a dartboard. Not a dartboard the size of a room or a city or a continent, a dartboard the size of the observable universe. Now imagine throwing that dart from a distance of 1 light year and hitting the bullseye. A bullseye the size of a proton. That is approximately the kind of precision we are describing when we say had to equal 1-to-1 part in 10 to the 60th at the Planck time. This is what physicists call the flatness problem. And for decades, from roughly the time it was clearly stated in the 1970s until a key development in the 1980s, it was one of the most unsettling open questions in cosmology. Not unsettling in a frightening way, but unsettling in the way that a good mystery unsettles you. The sense that something enormous is just out of sight, that there is a clue you haven't found yet. The clue, when it came, was called inflation. The basic idea was developed in 1980 and 1981, most prominently by Alan Guth, a young physicist who had been thinking about problems in cosmology and found a mechanism that, almost accidentally, solved several of them at once. The idea was refined and extended by André Linde and others in the years that followed, and it has been part of the standard cosmological toolkit ever since. It is not settled in every detail. Inflation is still an active area of research, and physicists debate the specific mechanism and the observational signatures, but the broad strokes are mainstream. Here is what inflation proposes. In an extremely brief period in the universe's earliest moments, a span of time so short that describing it in seconds requires a negative exponent with dozens of digits, the universe did not expand at its current rate, or even at the rate of the early Big Bang. It expanded at an almost incomprehensibly faster rate. Exponentially faster. The kind of growth where something doubles, then doubles again, then doubles again, not gradually, but in rapid, repeated bursts. By the end of this inflationary period, whatever small region of space the universe started as had been stretched to a size vastly larger than anything we can observe. Now imagine taking a small rubber balloon and inflating it not to the size of a basketball, but to the size of the sun. The surface of the balloon, which was curved before inflation, is now so large that any patch of it you can see looks essentially flat. The curvature is still there, technically, but it has been stretched to scales so enormous that from any point on the surface, you cannot detect it. That is what inflation does to the universe's geometry. Whatever initial curvature the universe had, whatever value started at, the exponential expansion stretches space so dramatically that any initial deviation from flatness is driven to unmeasurably small levels. Does not have to start at 1 to 15 decimal places because of some inexplicable coincidence. It is driven toward 1 dynamically as a consequence of the physics of inflation itself. This is enormously important and worth sitting with for a moment because it changes the nature of the question. The flatness problem, as we had it before inflation, asked, why did the initial conditions of the universe have to be so precisely tuned? Why did the universe begin with so close to 1? It felt like a coincidence you had to accept without explanation, a number set by hand to 15 decimal places. Inflation turns that question into an answer. The flat universe we observe is not a miracle of initial conditions, it is the predictable consequence of a mechanism. A dynamical reason, not a lucky draw. This is something to pay attention to, because it is the clearest existing example of something that looks like fine-tuning being dissolved by deeper physics. The flatness of the universe, which seemed to demand impossibly precise initial conditions, turns out to demand a mechanism instead. And while inflation itself is not without theoretical puzzles and unknowns, the point is that the question changed character once the mechanism was found. What looked like a tuning became a consequence. Physicists who work on the fine-tuning problem keep this example in mind. because it suggests that at least some of the tunings, the ones that feel most impossible, most precisely set, might be waiting for their own inflationary explanation. A deeper mechanism that makes the number inevitable rather than chosen. We will come back to that thought. Hold it for now. For the moment, let the flatness settle into you. The universe, balanced on its geometric knife edge. Inflation stretching space so smooth that the original curvature is buried. You, lying there on a planet, orbiting a star in a galaxy, able to exist at all because the density of the early universe and the geometry of space and the dynamics of whatever caused inflation all conspired, for reasons we are still working out, to leave us in a cosmos with the right shape. Now, 3. I want to talk to you about the number 3. In 1917, a Dutch physicist named Paul Ehrenfest asked a question that sounds almost childlike when you first hear it. He asked, why does space have 3 dimensions? Not 2, not 4, not 17. 3 large spatial dimensions. You can move left and right. You can move forward and backward. You can move up and down. That is it. 3 directions, perpendicular to one another, and the architecture of every physical experience you have ever had lives in those 3. Ehrenfest was not asking from idle curiosity. He was asking because he suspected the answer mattered. And the paper he published that year showed that it matters enormously. Here is the argument at its heart. The strength of gravity and electromagnetism of any force that spreads outward from a point source follows what physicists call an inverse square law. The force gets weaker as you move away from the source, and the rate at which it weakens is proportional to the square of the distance. Double the distance and the force is 1/4 as strong. Triple the distance and it is 1/9. This is not an arbitrary rule. It is a direct mathematical consequence of living in 3 spatial dimensions. Here is why. Imagine a candle burning at the center of a sphere. The light spreads outward in all directions. At any given distance from the candle, that light is spread across the surface of a sphere. The surface area of a sphere grows as the square of the radius, as the distance squared. So the same amount of light is distributed across an ever larger area, and the brightness at any point on that sphere falls as the square of the distance. 3 dimensions, surface area growing as distance squared, brightness falling as 1/distance squared. The inverse square law is, in a deep sense, a counting argument about how 3-dimensional space distributes things. Now Ehrenfest asked, what if there were 4 large spatial dimensions? Or 5? The surface area of the equivalent higher dimensional sphere would grow faster. The force would fall off faster. Instead of 1/distance squared, gravity and electromagnetism in 4 dimensions would fall as 1/distance cubed. In 5 dimensions, 1/distance to the 4th power. In each additional dimension, the force gets weaker with distance more rapidly. That sounds like a small mathematical difference. It is not. It has catastrophic consequences for orbits. A planet orbiting a star is in a constant negotiation between its forward momentum, which wants to carry it in a straight line away from the star, and gravity, which wants to pull it back in. The inverse square law in 3 dimensions allows a very specific class of stable orbits. Ellipses. Kepler's ellipses, the ones the planets in our solar system trace. These orbits are stable. A small perturbation, a nudge, and the planet wobbles slightly but returns to something close to its original path. In an inverse square gravitational field, Orbits are resilient. In 4 spatial dimensions, where the force falls as 1 over distance cubed, this stability disappears entirely. The mathematics shows that closed, stable orbits are impossible. Any planet nudged even slightly inward will spiral toward the star and fall in. Any planet nudged slightly outward will spiral away and escape. There is no zone of stability, no sweet spot where a planet can circle a sun for billions of years, quietly receiving the steady warmth that allowed life to establish itself over geological time. The planets in a 4-dimensional universe either fall into the star or drift away from it. The same argument applies to electrons orbiting atomic nuclei. The electromagnetic force in 3 dimensions allows the stable, quantized orbits that quantum mechanics describes, the electron shells, the energy levels, the structures that make chemistry possible. In 4 dimensions, electrons spiral inward and collapse into the nucleus. Atoms as stable structures do not exist. D equals 3. The number of large spatial dimensions equals 3. Ehrenfest showed in 1917 that this is not a cosmetic feature of the universe, not just the way things happen to be arranged. It is a precondition. In 2 dimensions, matter and gravity and fields behave so differently that the complexity required for any interesting structure is probably unachievable. In 4 or more large spatial dimensions, the inverse square law becomes an inverse cube law, or steeper, and stable atoms and planetary orbits become mathematically impossible. 3 dimensions is the answer. The others are ruled out by their own consequences. It is worth noting that string theory and some related approaches do propose extra spatial dimensions beyond 3. But those extra dimensions in these theories are curled up, compactified, at scales so small that they are undetectable at the energies we have access to. The large, navigable dimensions we move through remain 3. Ehrenfest's argument applies to large dimensions specifically, and the experimental fact is that the large dimensions number 3. The point stands. 3. A number that does not feel like it could be a deep question and turns out to be one of the deepest. Close your eyes and feel the 3 dimensions you occupy right now. The weight of the blanket pressing from above. The mattress firm beneath you. The walls of the room on either side. 3 perpendicular directions. The only architecture in which an electron can circle a nucleus without falling in. The only architecture in which the Earth can circle the Sun without falling in or flying off. You are not incidentally inside 3-dimensional space. You are possible because of it. And now, let us step inside the atom itself one more time, and look at something that is harder to picture but just as unsettling once you hold it in your mind. It is a problem that physicists call the hierarchy problem, and it lives at the intersection of particle physics and gravity, in the gap between 2 numbers that should, by most theoretical reasoning, bear some relationship to each other, and yet are separated by 17 orders of magnitude. The first number involves something called the Higgs field. You may have heard of the Higgs boson, the particle discovered at CERN in 2012 that confirmed the existence of the Higgs field. The Higgs field is not a particle. The particle is just an excitation of the field, a ripple in it. The field itself is everywhere, filling all of space, and it does something fundamental and strange. It gives mass to the other fundamental particles. The quarks, the electrons, the W and Z bosons, they acquire their masses through their interaction with the Higgs field. Without it, or with a different one, every fundamental particle would be massless, and massless particles travel at the speed of light, and massless particles cannot bind together into atoms or nuclei or anything stable. The strength of the Higgs field, its value in the lowest energy state, what physicists call the vacuum expectation value, is 246 billion electron volts. 246 GeV in the standard notation. This is the number that, through the Higgs mechanism, ultimately sets the masses of all the quarks and leptons, including the tiny mass difference between the up and down quarks that we talked about earlier, the difference that determines whether the neutron or the proton is heavier, and therefore whether the proton is stable. That number, 246 GeV, is the Higgs vacuum expectation value. Now here is the other number. There is a scale in physics called the Planck scale, named for Max Planck. The Planck energy, the energy associated with the Planck scale, is approximately 1.2 times 10 to the power of 19 GeV. Written differently, 12 billion GeV. Or written differently again, about 1.2 followed by 19 zeros in GeV. The ratio between these two numbers, the Higgs scale at 246 GeV and the Planck scale at 10 to the 19th, is approximately 10 to the power of 17. 17 orders of magnitude. If you want a picture of that separation, it is roughly the ratio between the diameter of a proton and the diameter of the solar system. Why does this matter? Because in quantum field theory, the framework that describes particles and fields and has been tested to extraordinary precision, quantum effects would naturally tend to push the Higgs mass up to the Planck scale. There are virtual processes, loops of particles appearing and disappearing in accordance with quantum uncertainty that contribute to the Higgs mass. Naively, these contributions should drag the Higgs mass up to the highest energy scale in the theory, which is the Planck scale. For the Higgs mass to sit at 246 GeV, 17 orders of magnitude below the Planck scale, these quantum corrections would have to cancel each other to extraordinary precision. Different contributions coming in from different virtual processes, all cancelling almost exactly, leaving behind only the tiny remnant we measure. This is, in the vocabulary of physics, deeply unnatural. Not unnatural in the colloquial sense, not strange or surprising in the way that an unusual personality is strange. Unnatural in a specific technical sense, which means that getting the answer requires enormous, apparently coincidental cancellations. Theorists find this uncomfortable in the same way that a careful accountant would find it uncomfortable to discover that a company's books balanced perfectly, not because the finances were healthy, but because 20 separate errors all happened to cancel each other out. The balance is real, but the process that produces it feels wrong. It suggests something is missing from the explanation. Physicists have proposed various mechanisms to address the hierarchy problem, supersymmetry, which pairs each known particle with a partner that cancels the quantum corrections neatly, extra dimensions at the TV scale, which could change the physics before the corrections become problematic, and other ideas. None of these proposals has been confirmed experimentally. The Large Hadron Collider at CERN has been running at the energies where supersymmetric partners would be expected, and they have not appeared. The hierarchy problem remains open. The cancellation remains unexplained. What it adds to our story tonight is this. The Higgs vacuum expectation value, 246 GeV, is another number that sits where it sits for reasons physics does not yet fully understand. and whose value, if it were very different, would produce a very different set of particle masses, a very different neutron-proton gap, a very different chemistry. It is not a number that lives at the Planck scale. It lives 17 orders of magnitude below. And that gap, that 17 order of magnitude quietness, is part of what makes the universe habitable. If the Higgs field were at the Planck scale, the quarks would have Planck scale masses, atoms as we know them would not form, and nothing downstream of atomic structure, molecules, water, biology, would be possible. The hierarchy, the problem, the puzzle, is also a condition. 246 GeV against 10 to the 19th. A tiny number against an enormous one. An unexplained separation that happens to be exactly what is needed for chemistry to work. Let that rest there. Let it be what it is. It is very late now, or very early. One of those hours when the distinction between late and early stops mattering and the night simply is what it is. Quiet and complete and yours. Outside, if there are stars, they are burning. Each one sustained by the gravitational balance against fusion pressure, each one itself a consequence of the roughness of the early universe, that 1 in 100,000, Q, the seed from which every star and every galaxy grew. The stars you cannot see are out there regardless. The flatness of the universe, stretched by whatever mechanism inflation used, curved by whatever geometry the early cosmos had before the exponential expansion erased the curvature, that flatness is present in the structure of the night sky, in the fact that the night sky has a structure at all, that it is not an undifferentiated fog or a set of giant black holes. The numbers we have been through tonight are not abstract. They are not the hobby of specialists with chalkboards. They are the precise measurements that describe why anything around you exists. The deuterium holding at 2.22 million electron volts so fusion can find its first foothold. The carbon-to-oxygen ratio sitting in its window because the strong force is what it is, and not a few % different, as Oberhammer and Kixt and Schlattel showed in 2000. The roughness of the early universe landing at 1 in 100,000 so that matter had just enough variation to gather into galaxies without collapsing into black holes. The flatness, tuned to what seems like impossible precision until inflation provides its dynamical explanation. 3 spatial dimensions, not 2 or 4 or any other number, because 3 is the one in which atoms stay together and planets hold their orbits. And the Higgs field sitting at 246 GeV instead of at the Planck scale, for reasons we do not yet understand. Keeping the quark masses small enough that nuclei can be built, that protons can be stable, that chemistry can exist. 6 numbers in Rees's formulation, 26 free parameters in the standard model of particle physics if you count more carefully. However you count, the same pattern, values that sit where they sit, in windows that allow complexity, in ratios and scales that permit atoms and stars and time enough for biology to do its slow, astonishing work. You have been carrying these numbers for a little while now. I do not mean that as a burden. I mean it the way you carry a song after someone has sung it to you, not because you have to, not because you are supposed to, but because something in you has recognized it and decided to keep it. The numbers are worth keeping, not because they prove anything about who set them, or whether they were set at all, or whether the question even makes sense. We will come to that. There is more to say about the honest answers physicists give, about what they mean and where the science ends and where something else begins. But that part of the story belongs to the quiet that comes next, in the last stretch of this long. Careful night. For now, let the numbers be numbers. 2.22. 1 in 100,000, 1 in 10 to the 15th, 17 orders of magnitude. 3. Each one a specific, measured, verifiable fact about the universe you are floating in. Each one a window, a condition, a threshold below which the next layer of complexity cannot exist. The deuterium allowing fusion, the density ripples allowing galaxies, the flatness allowing time, the dimensions allowing atoms, the Higgs scale allowing chemistry. Stacked up like that, they do not feel like coincidences. They feel like something. What that something is, that is the question. The real question. The one physicists genuinely disagree about, not because they are careless, but because it is genuinely hard and genuinely open and genuinely at the edge of what science can say. The breath comes in, the breath goes out, the room is still. Somewhere in the dark, atoms are holding together, electrons circling nuclei in the orbits that three-dimensional space permits. A process of such extraordinary ordinariness that it is occurring in every object within your sight and sound and reach. The same atoms that built up in stellar interiors. The same hydrogen that survived the first 3 minutes because the neutron-proton mass gap was what it was. The same carbon that formed in the triple alpha process because Fred Hoyle calculated that it had to. And then the energy level was found, and the universe obliged. You are not outside this story. You are not observing it from somewhere safe and separate. You are the part of it that can hear it told back and know, dimly, that something remarkable is contained in it. That knowing is itself one of the stranger facts in the dossier. But we will not try to solve that one tonight. Tonight, we carry the numbers quietly and let the dark do its work. So we come to it. The last number. The one that has been waiting in the dark since we opened this dossier. The one I told you we would carry across the whole middle of the night and only set down when we were ready. That loop has been open a long time. Let's close it gently, because it deserves to be handled gently. It is the strangest number in the set, and the story around it is the one that most honestly shows you where physics stops and something harder begins. The number is called lambda, the lowercase Greek letter. In Martin Rees's 6, it is the one he labels with that symbol, lambda, and what it measures, in plain language, is the push. The outward push of space itself, the thing that is, right now, making the universe expand a little faster each year than it did the year before. You cannot feel it. It acts on scales so vast that your whole galaxy and every nearby galaxy for millions of light years is too small and too tightly bound for the push to overcome the gravity holding them in place. But zoom out far enough to scales larger than galaxy clusters, and you see it, the recession, the stretching, the slow unraveling of the largest structures in the universe. That push has a name, dark energy. And the fraction of the universe's total energy budget it accounts for is roughly 0.7, 70% of everything. Lambda approximately equal to 0.7 of the critical density. That is the measured value. It was not always known to exist. For most of the 20th century, physicists assumed it was zero or so close to zero that it might as well be. Einstein had originally included something like it in his equations and then removed it, calling it his greatest blunder, and for decades the cosmological constant was treated as an embarrassing relic of a mistake he had made. Then, 1998 arrived. 3 teams of astronomers were measuring the distances to a particular kind of exploding star, type 1a supernovae, which burn with a consistent enough brightness that you can use them as what astronomers call standard candles, yardsticks spread across the universe. The logic is simple. You know how bright the explosion really is. You measure how dim it looks from here. The difference tells you how far away it is. What the teams were trying to determine was how fast the universe was slowing down. Gravity pulls. Everything in the universe pulls on everything else. You would expect the expansion born in the Big Bang to be decelerating, gradually, the way a ball thrown upwards slows before it falls back. What they found instead was that the distant supernovae were dimmer than expected, too far away, receding faster than the models predicted. The universe was not slowing down. It was speeding up. Martin Rees, Saul Perlmutter, Brian Schmidt, 3 astronomers working independently, arriving at the same impossible answer. The expansion of the universe is accelerating. Something is pushing outward, counteracting gravity at large scales, and getting relatively stronger as the universe grows and gravity's grip on widely separated structures weakens. Whatever that something is, it has the same character as Einstein's original cosmological constant, a kind of energy woven into the fabric of space itself, present in every cubic centimeter of the vacuum. Persistent, invisible, undiminishing. In 2011, Rees, Perlmutter and Schmidt shared the Nobel Prize in Physics for the discovery. Lambda was real, lambda was non-zero, and lambda was small. Astonishingly, beautifully, disturbingly small. Here is why that matters, and here is where we finally pay off the loop I opened at the beginning of this long, slow night. When physicists calculate what the cosmological constant should be, not observe it, but calculate it from the known behavior of quantum fields, from the way empty space at the quantum level seethes with activity, with virtual particles popping in and out of existence, they get a number. A specific prediction. One of physics' most confident mathematical results. And that prediction is larger than the measured value by a factor of approximately 10 to the power of 120. Let me stay with that for a moment, because numbers that large dissolve into abstraction and lose their weight if we do not slow down. 1 followed by 120 zeros. 120. If you wrote out the number 1, then wrote a 0, then wrote another 0, then another, and kept going, you would have to write 120 zeros before you had the right number. The ratio between what theory predicts and what we observe. The gap between what quantum field theory, one of the most precisely tested frameworks in the history of science, says the vacuum energy should be, and what the vacuum energy actually is. This discrepancy is commonly called the cosmological constant problem. It is, by the rough consensus of people who study it, the worst quantitative prediction in the history of physics. Not wrong by a factor of 2, not wrong by a factor of 1,000,000, which would itself be extraordinary. Wrong by a factor of 10 to the 120th power. That is not a rounding error. That is not a sign somewhere got flipped. That is something deeply, fundamentally unresolved about the relationship between quantum mechanics and gravity. 2 of the pillars of our understanding of nature that, in this particular corner, flatly refuse to speak the same language. And yet the measured value, the real value of lambda, is not 10 to the power of 120. It is tiny, small enough that galaxies formed, small enough that gravity had time to gather gas into stars and stars into clusters and clusters into the large-scale structure we observe. If the vacuum energy were anywhere close to what naive quantum field theory predicts, if lambda were anything like the calculated value, instead of vanishing almost to nothing, space would have blown apart before the first atom had time to form a molecule, before the first star had time to ignite. There would be no galaxies, No planets, no nights, no sleepy listeners. There would be an enormously energetic emptiness, expanding faster than anything could bind together. And then nothing. The fact that we exist at all requires lambda to be extraordinarily, implausibly, almost incomprehensibly smaller than everything we understand about quantum fields suggests it should be. That is not a slight tension. That is the largest quantitative discrepancy between theory and measurement that has ever been found in a quantitative science. Now, I promised you the honest version of this story. Not the version that leans forward and says it proves something, not the version that waves it away, just the honest version. Something you deserve to know before we go to the responses is that this problem, why lambda is so small, is not solved. It is not even close to solved. There are ideas, serious and carefully worked ideas, and we are going to walk through them because that is the point of tonight. But the why of lambda's smallness is, as of right now, an open wound in theoretical physics. The people who work on it are not pretending otherwise. They are working, and puzzled, and sometimes quietly amazed that we live in a universe where the mismatch is this severe and this unresolved. What there is, and this is interesting and genuinely remarkable, is a prediction that was made 11 years before the observation by a physicist who was thinking carefully about what the value of lambda had to be if observers like us were going to exist to measure it. In 1987, Steven Weinberg published an argument. Weinberg had already won the Nobel Prize in 1979 for his work on unifying the electromagnetic and weak nuclear forces. He was not a casual thinker, and in 1987 he sat down with what was then a speculative idea that perhaps the universe we inhabit is not the only one, that perhaps constants vary across some enormous ensemble of possible realities, and he asked a practical question. If the cosmological constant can, in principle, take many different values, what range of values could it take and still permit anything like the structures we observe? What is the anthropic window, the range within which observers could exist to ask the question? His conclusion, lambda must be small. Specifically, it must not be much larger than a few times the density of matter at the epoch of galaxy formation, or galaxies would be blown apart before they could assemble. It must be non-zero, likely, because a precisely zero value would seem to require an exact cancellation among the quantum contributions that nobody knew how to achieve. And so, by the logic of what a universe containing observers must be like, lambda should be small and positive in a range that at the time had never been measured, in a range that many physicists did not believe was real. 11 years later, Rees, Perlmutter, and Schmidt measured it, and the value was small and positive, and it sat within the window Weinberg had sketched. That is genuinely striking. A prediction made from reasoning about what the universe must be like if we exist, confirmed by observation, in a domain where the underlying physics had given no guidance at all. Whether it proves the framework Weinberg was using, the anthropic argument, the ensemble reasoning, is a different question, and I will tell you honestly that it does not prove it. Not in the way a laboratory measurement proves a theory. But it is suggestive. It is the kind of thing that makes serious physicists take the idea seriously. And that idea is response A. The first of the three honest answers. The one most people have heard of, though often in a form that is a little simpler than the actual physics. The multiverse plus anthropic selection. The core idea is this. If there is not one universe, but an enormous, perhaps infinite, ensemble of universes, each with different values of the fundamental constants, then the question of why our constants have the values they do becomes less mysterious. We are not a typical universe. We are not the most common kind of universe. We are the kind of universe in which the constants happen to lie in the narrow windows that allow complexity, chemistry, life, and eventually astronomers to exist. We find ourselves here not because this configuration was designed or destined or specially chosen, but because it is the only kind of place we could be. The selection effect. You can only observe a universe that permits observers. That statement, which sounds almost trivially obvious when you first hear it, is the seed of something called the anthropic principle. The term was coined in 1973 by a cosmologist named Brandon Carter at a conference in Krakow. Carter was careful to distinguish what he called the weak anthropic principle, which is simply the observation that our location in the universe must be compatible with our existence, from the strong version, which makes much bolder claims and is much more contested. The weak version is not really controversial. Of course, we find ourselves somewhere we can exist. You could not be somewhere you could not be. But the weak version does not, on its own, explain anything about the constants. For it to do real explanatory work, you need the ensemble. You need the multiverse. Where does the multiverse come from? In the serious physics versions. Not from imagination, not from speculation untethered to anything. It comes from two places, both of which have legitimate scientific pedigrees, though neither is proven. The first is eternal inflation. In the very early universe, in the first tiny fractions of the first second, something called inflation is believed to have occurred, a period of extraordinarily rapid expansion during which the universe grew from something almost unimaginably small all to something roughly the size of a grapefruit, in a time so brief that conventional language has no analogy for it. The inflationary idea was developed by Alan Guth, Andrei Linde, Alexander Vilenkin, and others, and it solves several otherwise awkward problems, including the flatness of the universe that we discussed earlier. The reason is so close to one. In some versions of inflationary theory, particularly Linde's chaotic inflation model, inflation does not stop uniformly everywhere. It stops in patches, each patch becoming what we might call a bubble universe, and the wider inflationary background goes on producing new bubbles indefinitely. Eternally, in fact, hence eternal inflation. Each bubble may nucleate with different physical properties, a vast froth of bubble universes, each with its own version of the constants, spreading through an inflationary background that never fully ends. The second place the multiverse comes from is the landscape of string theory. String theory, the framework that attempts to reconcile quantum mechanics and general relativity by describing fundamental particles as tiny vibrating strings of energy, produces an enormous number of possible configurations of the vacuum, the lowest energy state of space. Leonard Susskind, one of the architects of what he called the cosmic landscape, estimated that the number of distinct vacuum states might be approximately 10 to the power of 500. Each vacuum state would correspond to a different set of physical constants. 10 to the 500 is not a number the human mind can hold. It is larger than the number of atoms in the observable universe by an amount so vast that the comparison is almost useless. But if something like 10 to the 500 possible universes exist, each with randomly distributed constants, then the probability that at least a few of them land in the narrow windows permitting life is no longer vanishingly small. It becomes, in some sense, expected. That is response A. Stated fairly, it says, the constants look fine-tuned because we are in a fine-tuned patch of a much larger reality. Our patch is rare. The selection effect makes it inevitable that we would find ourselves in a rare, life-permitting pocket. Now, here is what I want you to hear clearly as the night gets quieter. The multiverse is a serious scientific hypothesis. Reputable, serious physicists advocate for it and work on its implications. But as of right now, it is not established fact. It has not been confirmed by observation. There is no measurement you can make with any instrument we currently possess that directly confirms the existence of other bubble universes beyond our own. The inflationary background that would produce eternal inflation, if it exists, is forever beyond our cosmological horizon. The string landscape has not been derived from first principles in a way that uniquely predicts anything we can check. The multiverse is a hypothesis, perhaps the most ambitious hypothesis in the history of science, and it may be right, and it may not be. The honest tag is untested hypothesis. I am not dismissing it. I am telling you the truth about it, which is what the title promised. Response B is quieter. It does not announce itself with grand machinery or with infinite copies of the universe. It says simply, we do not know enough yet. Every physical constant that has ever seemed like a brute fact, a number you just had to accept without explanation, has eventually often been explained. Explained in the sense that a deeper theory showed it was not arbitrary at all, but a consequence of something more fundamental. Johannes Kepler once tried to explain the distances of the planets from the Sun by nesting platonic solids, cubes and tetrahedra and octahedra in a geometric construction. He thought the planetary spacings were fundamental. They turned out to be accidents, consequences of gravitational dynamics and the particular history of how our solar system assembled. What looked like a special, meaningful configuration turned out to be one of countless possible configurations, with no deep significance. Response B applies that historical lesson here. Perhaps the constants are not free at all. Perhaps a future theory, something we do not yet have, something that would go deeper than the standard model and deeper than general relativity, would derive the constants the way we now derive the boiling point of water from molecular physics. Not arbitrary inputs. Consequences, necessities, the values they have, because a deeper law, which we have not yet found, makes them uniquely fixed. This would dissolve the fine-tuning problem entirely. If epsilon cannot be anything other than 0.007, if the neutron cannot outweigh the proton by anything other than 1.293 MeV, if lambda cannot be anything other than the tiny positive number it is, not because they were tuned by anyone, but because the mathematics of some deep final theory forces those values, then there is no improbability to explain. The numbers are what they are, because nothing else is possible. It is a beautiful idea. Physicists have been searching for it for most of a century. It has not arrived yet. There is no theory today that derives the constants from first principles. String theory was once hoped to be that theory, but the landscape of 10 to the 500 vacua suggests the opposite. Not one answer, but an enormous number of possible answers, with no principle to pick among them. Response B is not impossible. History strongly suggests that deeper explanations do emerge, that what looks irreducible often is not. But right now it is hope, not result. An honest tag, a legitimate scientific pursuit, not yet achieved. Response C does not try to explain anything at all, and in its refusal to explain, it says something important. There are two versions of it, and they are related. The first is the simplest thing you can say. The constants are what they are, and that is that. A brute fact. No further explanation. The universe had to have some values. These are the values it has. The question of why these values, rather than others, is not answerable, perhaps not even coherent. Scientists work within the universe. They describe what they find. The constants are found values, like any other measurement, and asking why the electron has the mass it has, rather than some other mass, is like asking why the Earth is the particular distance from the Sun it is. It is because it is. Some facts do not have reasons behind them. They are just the facts. That might sound like giving up. It is not, quite. It is a philosophical position that not every true statement requires an explanation, that the chain of whys must stop somewhere, and that perhaps it stops here. It is not a popular position because it offers no purchase, no project, no next step, but it is intellectually honest. It is what you are left with if you strip away the multiverse and the final theory. The second version of response C is sharper, and this is the thing I promised you much earlier, the intellectual twist, the part that most treatments of this topic skip entirely, and the part that I think matters most if you want to understand what the fine-tuning argument actually rests on. To call the constants improbably fine-tuned, you need to say that the probability of these values occurring by chance is very small. 1 in 10 to the 60th power, 1 in 10 to the 120th power, these are the kinds of numbers that get thrown around, and they are genuinely staggering. But ask yourself a quieter question. What probability distribution are you drawing from? When you say the cosmological constant had a 1 in 10 to the 120th chance of landing where it did, you are implicitly imagining a space of possible values, some range over which lambda could have varied, and you are saying our value is a tiny, tiny fraction of that range. But where does that range come from? Physics does not give us a prior probability distribution over the values of the constants. We have one universe. We have one set of measured values. We cannot, in any scientific sense, say what the probability was that those values would arise, because we have no ensemble of trials to calculate the probability from. And we have no theory that tells us what the underlying distribution of possible values looks like. This is called the measure problem, and it is, quietly, one of the most important honest cautions in this entire discussion. To call the constants improbable, you need a measure, a way of assigning probabilities to different possible values, and physics does not currently provide one. The apparent improbability depends entirely on the assumed range. If you assume constants could vary over the full range suggested by the naive quantum field theory prediction for lambda, then yes, the life-permitting values are a tiny sliver. But if the underlying theory, if response B's final theory, actually constrains the values to a much narrower range, or if the distribution is not flat but peaks somewhere near the observed values, the improbability could be much smaller or even vanish. Without a theory of what the constants could have been, the claim that they are improbable is not a measurement, it is an assumption dressed up as a calculation. That is not a reason to be unimpressed by the numbers. The numbers are real, and they are genuinely striking. But it is a reason to hold the word improbable carefully, and to notice that it is doing more work than the physics alone can justify. And now we reach the part of the night that, honestly, I enjoy the most. The skeptics. The people who looked at the standard fine-tuning story and said, gently but firmly, let us check that. Victor Stenger was a physicist and philosopher who wrote a book called The Fallacy of Fine-Tuning, published in 2011. His position was not that the constants are unimportant or that the physics is wrong. It was that the popular presentation of fine-tuning makes a specific mathematical error. It varies one constant at a time, holding all others fixed, and declares the result fatal. But real physics does not work that way. Constants interact. The stability of atoms, the burning of stars, the formation of heavy elements, these depend on relationships between constants, not the value of any single one in isolation. And if you vary multiple constants simultaneously, some of the combinations that look catastrophic when you move only one dial turn out to be survivable when the others shift too. Stenger built a computer simulation he called Monkey God. He varied several constants together, randomly, many times, and asked how often the resulting combinations produced universes with long-lived stars. The minimum requirement, more or less, for any reasonable chemistry. His results suggested that many combinations of constants, far outside the values we observe, still produce long-lived stars. Not all combinations, not most combinations, but enough that the claim of a razor-thin life-permitting window looked, in his analysis, overstated. The response from fine-tuning defenders was that Stenger had oversimplified, that his model missed important constraints. That is probably partly true. The debate is real and ongoing. But the point stands, single-parameter variation is not the full story, and Stenger took the trouble to show it with actual numbers. Fred Adams, an astrophysicist, published a thorough technical review in Physics Reports in 2019, titled with appropriate understatement as a study of the degree of fine-tuning in our universe. Adams approached it differently from Stenger, not a simulation, but a careful mapping of the parameter space governing stellar physics. His conclusion was that stars, functional, long-burning nuclear furnaces capable of providing the energy and timescales that life might need, can form and operate across a considerably wider range of physical parameters than the popular story implies. His rough estimate was that something like 25% of the relevant parameter space allows stars to exist, not a sliver, not 1 in 10 to the 60th, roughly a quarter. 25% is not a guarantee of life, and Adams was careful not to claim it was. Allowing stars is not the same as allowing carbon, or water, or amino acids, or brains. The window for life, if you include all the necessary conditions rather than just stars, may indeed be much smaller. But the point is that the dramatic version of the fine-tuning argument, the version that says change any constant by even a tiny fraction and the universe dies, does not survive careful scrutiny without significant qualification. The windows are real, the sensitivity is real, but the sharpness of the windows and the universality of the single-parameter variation argument is something careful researchers push back on. You deserve to know that. Sabine Hossenfelder is a theoretical physicist who has made it her particular project to examine the assumptions physicists make without always noticing they are making them. In her book Lost in Math, published in 2018, she argues that fine-tuning and its cousin concept, naturalness, the idea that a theory is suspicious if its parameters require precise cancellations, have been overused as guides in theoretical physics. These aesthetic criteria, she argues, are intuitions, not laws of nature. They feel like they should constrain reality because they feel wrong, the way a scale with one side, obviously heavier than the other, feels unstable. But the universe does not have an obligation to satisfy our intuitions about what feels balanced. Hossenfelder is not denying the physics. She is questioning whether the sense of wrongness we get from fine-tuning is a reliable signal of something to be explained, or whether it is a pattern recognition instinct that happens not to apply at the scale of fundamental constants. She is a dissenting voice from within the physics community, not from outside it, and she is a voice worth hearing. And then there is Douglas Adams, not the physicist, the novelist, the man who wrote The Hitchhiker's Guide to the Galaxy. He told a short story, not a formal argument, just a thought, the kind that lands so cleanly it has been quoted by actual physicists ever since. "Imagine a puddle," Adams said. "The puddle wakes up one morning and thinks to itself, 'This hole I am sitting in is a remarkable thing. It fits me perfectly. Every curve and contour of my shape is exactly matched by the hole. The fit is so precise that it seems impossible to imagine it was not made for me.' The puddle concludes, with great satisfaction, that the hole was designed with it in mind. Then the sun comes out, the puddle evaporates, and the point is made. The puddle is not wrong that it fits the hole. It is wrong about the direction of causation. The puddle is shaped by the hole, not the other way around, and the error is undetectable from inside the puddle. The puddle has no access to the existence of other holes with no puddles, to the vast landscape of holes that went unfilled, to the rain that fell and gathered and did not wonder and simply was. The puddle can only observe the hole it is in, and from that observation it draws a conclusion that feels irresistible and is wrong. The anthropic caution says, be careful that you are not the puddle. You exist in a universe with these constants. You find the constants remarkable. You cannot observe the vast space of other possible constant combinations, the universes in which nothing formed, the vacua in which no complexity arose, the configurations that produced no one to find them unremarkable. You only see the hole you are in. That does not mean the fit is unimpressive. The fit is genuinely impressive. But the fact that you observe it does not tell you, without additional argument, whether the hole was carved to fit you or whether you simply happen to be the moisture that gathered here. So let us stand, quietly, at the edge of what physics can honestly say. The constants are real. Their measured values are real. The sensitivity of a life-permitting universe to those values is in many cases real, though the sharpness of the sensitivity is debated, and the single parameter framing overstates it in ways that serious researchers have documented. The cosmological constant problem is real and unsolved, and the discrepancy between the naive prediction and the observed value is the worst quantitative gap in modern physics. Weinberg's 1987 prediction was genuinely predictive and was genuinely borne out. These are things science has actually established. The three responses, multiverse, final theory, brute fact plus measure problem, are each intellectually honest. Each is advocated by serious physicists. None is proven. The multiverse is a live and carefully developed hypothesis that currently has no direct observational test. The final theory is a legitimate scientific aspiration that has not been achieved. The brute fact response, including its sharper form in the measure problem, is a philosophically coherent position that reminds you the apparent improbability of the constants rests on probability distributions we have not derived and cannot currently justify. Here is where physics ends, as best I can draw the line for you tonight. Physics ends at the measurement. The constants have been measured. Their consequences have been calculated. The sensitivity of various outcomes to changes in those constants has been modelled with the honest caveat that the models are simplified and the windows may be wider than the most dramatic presentations suggest. The cosmological constant problem is a real open failure of reconciliation between quantum field theory and observation. That is all physics. That is what the instruments and the mathematics have returned. What physics has not returned, what it cannot currently return, is an answer to why. Why these values rather than others? Why there is something rather than nothing? Whether the ensemble is real? Whether a final theory will fix the constants or leave them free? Whether the improbability is genuine or an artifact of a measure we invented? Those questions are at the boundary and past it. Some of them may eventually become physics questions as new theories develop and new observations become possible. Some of them may be philosophy's permanent territory. The honest answer is that we do not know which is which yet. What you can take with you into the quiet, and this seems to me the right thing to carry into sleep, is not an answer, but a texture. The texture of a universe that, at its most fundamental level, is structured around numbers. 6 of them, in Martin Rees's framing, though the full accounting runs to something like 26 free parameters in the Standard Model alone. Numbers that could, as far as current theory can tell, have been different. Numbers that, at the values they are, allow a particular kind of richness, atoms, molecules, stars, time, chemistry. The conditions that allowed something to emerge which can now sit in the dark and hear this told back to it. The richness is real. The numbers are real. The question of whether they were set or selected or simply are is not yet answered and may be the most important question our species carries forward into the next century of physics. There is something genuinely moving about that, if you let it land. Not terrifying, the title said terrifying, but sitting here, at this hour, with the night doing its work around you. I find it less terrifying than it sounds in daylight. What it feels like now is large. Large in the way that a clear night sky is large. You look up and the scale exceeds everything familiar, and for a moment that is vertiginous, yes, a little like falling. And then something settles. The scale does not diminish you. You are part of it. The fact that it is so vast, and that you are in it, measuring it, telling stories about it, building equations that describe its deep behavior, that is not a small thing. That is, if you think about it, the most extraordinary consequence of those 6 numbers being what they are. A universe in which anything at all is possible eventually gets around to beings who want to know why it exists. Whether or not that is a coincidence, it is the fact, and the fact, held quietly, is enough for one night. I want to ask you something before we close. Not a test, not a debate. Just the question the dossier leaves you with, and leaves me with. Of the 3 honest answers, the multiverse, the final theory, the brute fact, which one sits most comfortably with you? Not which one do you think is true, because none of us knows, but which one does your mind reach for, instinctively, when you hold the numbers and feel their weight? That is the question I would like to leave open, the way you leave a window open, just a crack in the summer, not for any particular reason, just because the air outside is worth keeping close to. The cosmological constant sits at 0.7 of the critical density, off from the naive prediction by 120 orders of magnitude. And galaxies formed anyway. Weinberg looked at that problem in 1987 and said it has to be small, and it was. The neutron outweighs the proton by 0.14%, and every atom in you is built on that gap. The carbon in your cells came from the triple alpha process, from energy levels Fred Hoyle predicted from the fact of his own existence, from stars that burned slowly for billions of years because gravity is 36 orders of magnitude weaker than the electromagnetic force. The density ripples in the cosmic microwave background were 1 part in 100,000, rough enough to seed galaxies, smooth enough not to collapse straight into black holes. Space has 3 dimensions, and Paul Ehrenfest showed that in 4 or more. Stable atoms and stable orbits are not possible, and without stable atoms and orbits there is no chemistry, no biology, no dark room with a lamp on somewhere nearby. All of that, tonight, all of that carried from the hook to here. That loop is closed, that promise is kept. And the honest resting place, the place physics leaves you, not a cliff, not a landing, just a wide and truthful plateau. Is this, we know what the numbers are, we know what they allow, we do not yet know why they are what they are, or whether that question will ever become the kind that physics can answer. And that not knowing, held without anxiety, is itself a form of wonder. The question is open. The universe continues. The search continues. And you were here for a little piece of it. Good night, kiddo. Gramp'll leave the porch light on.